Okay, we're not going to waste any time because we got a big deal here, and but it breaks into two parts. The first part here is a discussion of linear versus nonlinear resonance, or so-called parametric resonance. We're going to spend a good part of the class talking about that. And this is going to tie a lot of things together: quantum mechanics, classical mechanics. It's going to tie together the trebuchet, the atlatl, and a few things like that that like to throw things fast. So the quantum mechanics and band theory, you wouldn't think they have anything to do with these ancient mechanisms, but I'll show you that they're quite analogous in certain situations. Then we're going to come back and redo our normal mode theory using the symmetry analysis, and show that when you do that, you get some incredible power to see some really neat phenomena. Already I've shown you beats with C2. Well, we're going to see what C3, C4, this means cyclic symmetry of order 3, 4, 5, 6, 7, and higher, make super beats, which are called revivals in quantum optics and quantum information theory, actually, is what we'll be talking about. Anyway, here's where we start the first part. We've already done a forced, actually we did damped, this time it's 0, frictionless, a forced, a stimulated, stimulus frequency oscillator of a certain natural frequency that would go, and in this case, be infinitely excited at the point where omega s was equal to omega 0. But we talked about very high quality oscillators such as atoms that were excited by factors of a million or more. That's the linear or additive resonance. And you remember how it grew linearly in the phase plane. It gained its velocity linearly with time as you were pumping it, assuming you were on resonance, right? And that's just because when you force something at a constant rate, its velocity goes up with a constant rate. So you're talking about a constant acceleration, basically. So this is the contrast, to be contrasted with this nonlinear or multiplicative resonance. Example, we're talking about the magnetic field making a cyclotron orbit. Well, if you want to change the B, that's a parameter now, but the oscillation that's associated with it, if you're going to wiggle it, is multiplying, not adding to the oscillation in progress. So this little equation here describes what's in the very last chapter of Unit 4 on resonance, and this is called parametric resonance. So the reason is pretty obvious, because it's a frequency parameter that you're going to be wiggling. Not we kept this thing constant when we did our linear resonance. Now we're going to be wiggling it. But you should be aware that this parametric resonance is analogous to Schrodinger-like equation. Okay?
Dr. Harter, but this equation is second order in time, right? Unlike Schrodinger equation, which is first order in time.
That's right. That's right. If I were to replace this with an x, I would have Schrodinger's equation. That was the independent variable. Here it's going to be time. Okay?
Oh, okay.
And the thing that's most, I should say, the device that's most easy to show this is just a pendulum. Okay? But people that have glasses that don't have these things attached to it can take their glasses and do this, right? This sort of thing, right? So twiddling is an example of really both of these resonances. But the idea here that if I'm asked to get this resonating, and I go, put it on dead center here and make it stop. So I stop it, and then I go, it's pretty easy for me to get that thing going, and it's of course increasing linearly with time. Okay? So that doesn't require much skill. What really requires skill and some initial oscillation, that is, it has to be going already, but to do this, doesn't look like much is happening. It's pretty hard to make this happen. Now we're going to show a simulation of this thing happening big time. If you can do this right, you get an explosion here. It explodes exponentially.
So you mean to say the bob oscillates vertically as well as it
We're
swings?
going to oscillate the parameter of the coefficient of this oscillator, you see. It already had a value G over L that makes it swing, right?
Yeah, right, yeah.
Okay? In the Schrodinger equation, that'd be like E. This is like V, the potential that varies with distance. But it's time now that we're going to make this vary. Okay?
So, Dr. Harter?
So I get this thing going, and then I go like this. And you can see it's doing something, but it's not resonating. It takes a lot of skill to make this resonate.
Okay.
You see the difference?
So if the bob oscillates vertically in addition to swinging
The fulcrum,
horizontally,
the actual fulcrum.
So in that case, then,
This one's easy.
Yeah.
We have a natural way I can make that happen real easy.
so in the second case, then potential energy changes at every instant, right? Because the fulcrum itself is vertically oscillating
Right.
back and forth.
It puts it in a moving frame. This is an Einstein elevator gone crazy. Okay? It's jerking up and down. Okay? So sometimes the gravity is really strong, and then sometimes it's very small or negative even. And I'm going to imagine this is a lever that's strict, so when I go really fast, I could literally be pushing that lever. Okay? So that's the deal, is that you're in an accelerated frame.
So that would
That's
be
being
required.
added to what the gravity's doing to you.
That would be required. You couldn't actually get it to work with a string, even if you were really good.
Being really good just depends on you learning what frequency should be useful. Now, after class, I'll ask, you can demonstrate it with these pendulums by simply taking that pendulum, this I discovered quite accidentally, and just start walking. You can't stop this phenomena then. It will hit you. Not that hard, but it will be really hard. And most people would say, that's just an annoyance. Why can't I carry these pendulums down the hall without the damn thing hitting me? But you can't. You're in what's called a band gap, where the motion is unstable. And that's what we're going to now analyze.
Physically, what is A by of t? What function? What does that function tell us? Physically, what quantity is that?
A of t is going to be A constant times the cosine of t. So we're going to restrict ourselves, just as we did over here, to having a sinusoidal motion of some frequency. Okay, I did a pretty good job there. I started to get it. Okay.
Oh, it's okay. So y is A times cosine omega t, something
Yes,
like
it's going to be, this is going to be a constant times cosine of t. Okay? Now, as I said, the general case is a really nasty equation. We're working on the in-between here. Okay? But the other thing I want to point out is finding the right motion to do this in a sport that involves a lever, like a baseball bat or a tennis racket or a golf club, is the secret to being good at it, to getting a lot of energy into it. Okay? And we'll see moments when the simulations of these things, all of a sudden, a burst of energy shows up at the end of the motion. Okay? So, Trebuchet does this. Well does, Trebuchet is taking advantage of this. We hope to build one that will demonstrate the two different kinds of resonance. The usual pendulum resonances here, And the vertical one that's got the exponential behavior is here. Here's what I call the Arkansas whirler. It's a stick with some notches on it, and you, how many people have seen this at a gift shop? You take a pencil and, you know, on the thing here, and the little nail here is stuck into the end, and a little propeller on it. And if you do it just right and hold it just right, this thing will just take off like a fan. Okay, so there's a good example of parametric amplification. And I tried to find mine. I can't find it, so I can't demonstrate that one for you. I'm going to have to make a new one. Okay, so here's the deal. To answer your question, Bailey, this is what we're going to put in for our Schrodinger wave equation. We're going to put in a periodic potential, the simplest one, the cosine. Okay?
Can you just go to the previous slide, Dr. Harter? I just have a question. The slide where you had that figure. Yeah. So in this one, for the figure that Y stimulated pendulum, for example, if I want to write down, say, the Lagrangian for this system, then I know that I can use polar coordinates. L is constant, the length. So I can say that X is, say, minus L sine phi, and Y is L cos phi. Mm-hmm. But in addition, we also have that vertical thing, so Y should be L cos phi plus A cos omega.
Your Lagrangian is going to have explicit time dependence.
Right, because of A cos omega t.
Yes, right. In the nastiest place.
But one thing that I don't understand is how will I write down my potential energy, because the fulcrum is, that reference line itself is oscillating.
Potential kind of goes out the window, doesn't it?
Well, that's what that's not clear to me. Why?
You messed it up. You're making your local potential time dependent. So just, you know, potential is not a useful concept in this case.
So, in this case, physically, so how
force is.
Yeah.
And the Lagrange equations, remember I said Lagrange equation of the first kind there, where you put the force explicitly. Don't try to make it a potential.
Okay. So which means it's better
still
to solve.
Work.
So you mean it's better to use Newton's laws of motion to solve this problem? Right?
You could. And that's essentially what we're doing. We're saying, I'm on an elevator, and I've got a gravity that's doing this.
Okay.
Right?
Okay. Okay, so effectively then we solve this differential equation.
Yeah. You got a nonlinear differential equation.
Oh my God.
Yeah.
I was trying to avoid that.
Yeah. And actually it's worse than that, because we're going to just take it for the case where the phi is small. Normally you'd be putting a sine phi, and you'd be working with the sine phi variables, and when we plot these things, actually we'll list it that way. But that has to be done numerically.
And one small question, from where did we get it? AX of t, AY of t, is that vertical?
Yes. And then this is AX. You see, it's influencing that thing depending on the cosine of this angle. Starts out fully effective with cosine equal to 1, but if it's at 90 degrees, it's going to be doing parametric amplification the other way, right?
Are we having
yeah, don't worry about this one. This is nasty. Let's just do this one and this one.
Okay.
Okay, we got enough to do with this thing. Okay, so here's the deal. All right, and we have this one on a periodic roller coaster of some kind. That's one way you could do this. Is just, you know, be going up and down on some sort of ride at the amusement park that was perfectly cosine. I know that'd be tough to make, but we're gonna. That's the case we're going to take. And then this thing right here is the actually called the Mathieu equation. That's when you put a cosine in for the potential. So this is the beginning of band theory for electronic waves in one dimension. Okay, and then there's this thing that is the jerk pendulum trebuchet model. Okay, for we're going to, you know, imagine the angles don't get close to a radian. They're going to stay below a radian. But once it starts, it goes anyway, whether it's big or small, as you're going to see. So we're going to replace nx here with omega yt. That's the connection relation for the independent variable. And if that's the case, then nx dx over omega y is dt. okay? And the dt squared is right here, so I'm going to have an n squared omega squared dx squared is dt squared. So I'm going to replace this guy over here with that, okay, to make it so they're the same, okay? And as I am going to explain later, we're going to stick with n equal 2 for a lot of our things. This is the way you get the band edges, and the over there it has a significance in time that's important for understanding this. So here's the second order equation with the x in, and there's the nx in there. So this is an equation that we're looking at. Okay, just to make it like that one. Okay, and while we're at it, this G over L, well, that's the energy. Okay, we're going to be looking for very special values of this energy. They're called eigenvalues, and in fact, there's a band of spectra associated with this one that you've probably heard about. That's the way our semiconductors and various sorts of laser diodes and things like that make use of that resonance. So there is that part of it. And then this right here is the potential. You see, and all we have to do is note that this coefficient of the cosine potential is equal to a parameter over here. Now that's a complicated little connection right there. Okay? That VO here is equal to the whatever is multiplying the cosine. And the omega y cancels out. So the coefficient that we're talking about right here is n squared ay over the length of the pendulum. So I'm going to set to 1, just to keep, I'm going to give me the gravity 1 and the pendulum 1, just to keep things clean here, so we can go rapidly. But we're hoping to actually make a device that shows this. I've been putting this off way too long. We should have the devices I have diagrammed there sitting here right now. Next year, I promise that we'll have that. But in the meantime, we're going to go about the mathematics. So the Schrodinger potential is 0, and there's no stimulus on the pendulum. We start back with the same equation, essentially, where the energy now is just the G over L, the omega 0 squared for the pendulum, which is 1 in our thing that we're going to be doing. And the eigensolutions for this one are the familiar, well, for this one, familiar to you as Bohr orbitals, or the familiar phasor oscillatory. Call it a wave. It's a wave if it oscillates, right? So just this thing right here is analogous to this thing right here. Remember, this is space variable, this is time variable over here. Okay? And we're going to be working on a device over here that behaves like this under certain conditions, which basically are small amplitudes. Okay, now if you have periodic boundary conditions, that is, if you put this equation in a box of a certain length so that you're stuck between 0 and L, you know what you have to do here. You have to say, I'm interested in eigenvalues that are discrete. I'm interested in k values, that's wave number value, wave vector here. That's with the 2 pi. If it wasn't a 2 pi, it'd be a wave number, kappa, that we talked about in that talk on relativity. This one has got a quantum number m associated with it, an integer value, in order to fit in that box. And we're going to ask the pendulum to do the same thing. Now, this is a little harder to do, but we're going to have a timer that goes off at a certain time t and says, hey, I want you to stop, and I want you to be equal to 1 at that point, or equal to 0, or something. I want you to repeat yourself after each one of these intervals. Okay, I'm going to demand only those solutions, just like here. It's pretty obvious why we demand them here. It's not obvious that I would demand that here. But I'm demanding it because this analogy is so powerful for doing band theory. So we're going to get the time band theory that way. So the limit L equal 2 pi equal t for both analogies you see, will be E equal K squared, okay? 0 squared, 1 squared, 2 squared, 3 squared, 4 squared. And basically this one's the same thing. And the K can go either way, so this is really plus and minus as well as this one is. Okay, so that's where we start with this stuff, and I'll point this out again later on. So the Schrodinger equation with non-zero potential is solved in a Fourier basis. I'm going to imagine it's linear combinations of e to the I kl with k equal to some multiple of 2 pi over L. I'm going to make a Fourier series of those harmonics. Okay? And when I do that, I get a really nice representation. I get a very simple, and what I want to do is move all of this up to the top of the screen, but here are the matrix elements of this cosine potential, this cosine of nx, which we're eventually going to make 2x, because n equal 2 is what we call the band edges. The stuff inside the band, we're not going to care about that for a while. Just want to get the outside, and see where the band gaps are, where the band boundaries are. Okay? So by putting 2 in here, I get that. You'll see why a little bit later. And anyway, really simple matrix elements. So let's move all this to the top of the screen. And while I'm at it, let's advance the other one so that it shows what we do. Let's review what we're doing here. That's what we're doing. We're trying to make an analogy. And we're trying to make an analogy between a Schrodinger wave equation and the jerk pendulum equation. First we match the independent variable x on the left and t on the right. And then we make a connection relation of the differentials. So we get an equation that looks like the one on the left, but with the parameters on the right. And we notice we have connection relations between eigenvalues of energy and inverse square frequency values associated with the pendulum that is being jerked. And then the jerking amplitude is related to the potential. That's a little bit easier to see. But through an n squared. So if we use n equal 2, we're going to have to put 4 there. Okay? And then we're going to do the band theory with just plain waves on the left and just plain old frequency Fourier harmonic components on the right. Okay? So that's the stuff that I'm talking about right there. We're going to use a matrix to do that. So we're going to reduce this to a matrix eigenvalue problem, which nowadays is really easy to do on a computer. But you can do some of this, you can just go in there wherever you're interested and draw a 3x3 matrix around there and solve that, and you'll get pretty close under the conditions that they knew here, this off-diagonal part, the off-diagonal part being this, here it is, being this amplitude of the oscillations in the crystal potential, how big the amplitude is, okay, which is, in this case, 2 squared over 2 times AY. That's 2 times this acceleration of the pendulum that we talked about, divided by, and this is going to be 1, so forget about it now. Okay? So this is what we're dealing with. This is the problem that we need to treat by computer most of the time. I'm going to do about 8 of them at once to get some of the answers that we're getting. And I don't recall if we thought about putting this in the Jerkit application, but I think we ought to. I think we ought to really juice up that one. We have sort of a crust of this in the old-fashioned way, which I'll be demonstrating. But it's numbers like this that I want to get. Say for V0 just equal to 0.2. That means that this little v is 0.1. Okay? And so I'm just doing that matrix. I took about, what do we got here? 1, 2, 3, 4, 5, 6, 7. I think I took about 10 dimensions and diagonalized that, and these are the numbers come out. And they're good. These are really good. These are probably good to 6 or 7 figures, and they start to go down This one's probably only good maybe to 3 figures or 2 figures in this particular case, but that it's good enough for us to see how this works. You always have to truncate these infinite matrices. That's the art of numerical analysis in modern physics. Okay, so that's what we're after. Now, it's funny about this one though, when we're doing this connection, there are some things about it that are very anti-analogous, and we're about to see that. What's going to happen is that there's certain of the pendulum states, and we're starting with a pendulum here and just talking about it jiggling very little, but there's a whole bunch of states, which I've colored in turquoise blue here, where the pendulum is inverted. And normally it would fall over, right? We always studied that business, right? The phase space is hyperbolic, okay? And the motion would be hyperbolic sine and cosine solutions, right? But we're jerking this thing up and down, and if you do that right, and this thing's going to tell you when you can do that, these that are marked here are stable, inverted states of this pendulum. And this brings up another sport which I do not recommend, and that's called riding a unicycle. Or another one which I really don't recommend, which was achieved by the person in a movie called The Wire. Anybody know about that? You really ought to get that movie and look at it. This is a tightrope operator, or walker, that is so good that he got into the World Trade Center before it was bombed, strung a cable between the 2 towers at 1,100 feet or 1,400 feet or whatever it is in the air, and began walking on the cable one morning, Saturday morning. And he even got out in the middle, and he got down and he was on his back, lying on the damn thing. Then he got back up again. By this time the police were there, and he would walk over to one of the towers, and the police would try to grab him. He'd say, "Aha, you didn't get me." And then he'd go over and do the same thing on the other side. This is somebody that really knows how to do this frequency. He's able to balance himself stably in a completely unstable situation. To me, this is absolutely incredible.
Once again, so what is that mathematical condition for?
Well, this is what we're trying to solve. Okay.
Yeah. You know, like if you want to remain stable in an unstable environment, so.
That's right. These are the magic numbers. You've got to be wiggling the amplitude of your up and down. That is, you've got to be springing yourself with your toes, I guess. Okay. You're on your toes, but he's able to do it lying down. Okay? I mean, this is amazing. But, you know, unicycle riding, too. In order to stay, you've got to be rocking. What's the frequency that you rock? It keeps you stable. And there are people that can do that with unicycles that are twice the height of this room. So this is very important physics for these people, right? That we're talking about here. And we're going to see examples of it in just a minute, okay? But whenever the E value for this band theory goes negative, you've got an inverted stability. The rest of the time it's just hanging down there stable. Which is also amazing, because we're going to be jerking the thing up and down with considerable amplitude, and it's stable. It stays, it doesn't explode. You see? Those are called the stability bands in band theory. That's where the wave function actually lives. Outside of there are called the gaps, and that's where if you put a wave in there, it explodes exponentially and disappears. Okay, that's what we're going to see. We're going to see that in some detail here. In fact, there it is. These are the actual band edges that we're getting with those numbers. Now, I've just picked a certain value of the amplitude of the V. This is how the bands evolve as you make the potential V bigger and bigger and bigger. And this is sort of a line that indicates how big the potential is. So everything, all of the quantum states below this thing are tunneling states between the different barriers caused by the potential that's this high. And then down here, these things are all living above the band and feeling its effects, and that causes this sort of tongue to go out there. And these things below it, including the ones below the axis, which are going to be the inverted stable states. Okay? So here's our relation of the V amplitude, which is this thing, to the AY. That's just going to be constant. They're basically linearly related. And then over here is the, let's see, that's the VO. Again, here's the frequency omega. It's the square root of the inverse of the eigenvalues that we get by solving that matrix from this equation. This is our connection formula, and that's the inverse of it. Okay? So that's what we're dealing with. And I want to look at just a couple of solutions right around in here and maybe here. And these are things I'll let you play with it when we get the app working. You're welcome to borrow a computer that has the app working from the old programming methods. Okay? So there are the numbers. There's the picture of energy bands versus potential height. And here's some of the solutions which we're going to go through now. Okay, just to get a feeling for them. I'm going to start with the unstable one. I'm going to start, and remember the relationship is inverse energy gives you pumping frequency. Okay? So let's go over here, and now we're going to be looking at the screen to the right of this screen, in which you see already a picture of a potential in light blue and a wave function that could live in that potential in the case of a crystal. You see, this would be one of the ground state eigenfunctions of a crystal in one dimension that has this property, and this is it right here. And there is the actual motion of the pendulum that will make this. And that's kind of a nice motion. If you can keep that frequency, this thing will not, you will not fall off the wire into the street below the World Trade Center. This is one of them. Now, you see, the point is, it isn't just one. If you make a little bit of a mistake this way, you're okay. If you make a mistake this way, you're going to start to blow up. So you got to come back into this region when you're playing this game. Okay? Now, you think I'm kidding here. Let me just pull this thing off to the side here so you can see how it behaves. Okay? I'm going to go ahead and just start it right about there at that angle. Okay? Now I'm pulling on the thing so it accelerates. That's the way to accelerate it. And I'm going to pull on it again so it really, but then I stop and now I accelerate again. Now I really go up, you see. So this is what it does most of the time. This is the behavior of this thing. It's almost always chaotic. It's like our trebuchet for the Siege of Kenilworth.
But Dr. Harter, I have a question. The problem that we have is we are just oscillating that fulcrum up and down.
That's what we're doing.
Yeah, but here that bob, what is that? Is that?
There's the pendulum.
Yeah, but we in that case.
I'm just plotting, on all of these I'm plotting sine of phi.
Okay.
Okay, which is very close to phi if I keep phi small, but it isn't if phi is big. So that's what's going on there. Okay? Now I can bring this thing back and start it again with, you know, any amplitude I want that's small, and I'll get the same thing. Let me start it again right next to there with a smaller amplitude. Okay, about half of that. I've got to be careful here.
Oh no, my question was like, can we assume that the pendulum swings about the fulcrum because it just oscillates until its extreme points, right? It doesn't complete the circle, does it?
Oh, it's chaotic motion. Once you get out there into the phase space,
Okay.
and we're just doing this, that's all we're doing, right? That's the only meddling we're doing, right? That is not changing at all, okay? But every once in a while, we just catch it at the right place, boom, it takes off. Or if we have the right frequency and it happens to be in the right place inverted, it stays there for indefinitely. Forever. Okay? So, you know, on either side, right? I can put it over here on this side. Same wave, disproportional to the other waves, right? Same wave. And there's a little potential that's causing it. The light blue, right? So there's a band eigenfunction. Right there. And it's repeating every period. So that's what you get with n equal 2. 2 points, 1 period. Okay? All right, let's look at another one that's on another portion of this band. We're basically in here someplace. We're going to look at one that's real close to 0. That means it's going to be a big number when you invert it. Let's try that one. I think that one is the next one here. Band edge 1 minus is what this would be called. And that's this one right here. Okay, see it? Now this one is really stable. The other one blows up if I go out here too far, but this one I can take it way out here, and it won't be quite right. It won't match the, you see it's missing the period thing a little bit there, but it's still stable. It goes all over the place. But as long as I keep it small, it will mimic that wave that we did the first time there. And it'll do it on either side. You see. You know, and obviously you want really small angles if you want the thing to behave, you know, nicely. But there it is with a minus sign. Same thing. Okay, so this is a really stable one. And I can change the frequency between these two and be guaranteed that I'm not going to fall off of my perch. That's a stable region right there. That's what it means to be a band of possibilities. And all of the other energy states that are in there just have different periods. Different wave numbers if you're talking about the actual band theory of the solid state. Well, let's keep going here. The next one is going to be starting up above here, okay? And that one is this band edge right here. Now this one you have to do upside down. This is in the positive energy region, so it's going to make a sort of square wave like this. You see that? And basically it's dragging the thing back and forth on what forms kind of a parabolic looking curve. Far from being a parabola. It's more like a hyperbolic function. But that is very stable, and any amplitude I put in there that's below that is going to work forever. This thing is not going to explode. And then on the other side of that band, we're at this one right now. On the other side of the band is another one that also has a period equal to that of the lattice. That's what you get when you have big N equal to 2. Okay? So let's take a look at that one real quickly, and then we'll move on. We already looked, I got to remember which one I'm here. It's this one right here. Now just remember that as we go up in E, the wiggle frequency approaches 0. Okay? Way up there, right? So it's very slow. This is very slow. You got got to stay slow for these guys. As long as you stay slow, it won't blow up on you. Start doing this, and it will blow up, because you'll be winding up in the gap region here. Okay?
Dr. Harter, why do you have modulus of E for omega sub y?
Why do you have
The modulus of E, because
the modulus
of E. Yeah.
Oh, because I don't want to get imaginary omega
No, but since you're dealing
in our
with
connection.
Since you're dealing with an oscillator, energy is always positive, right? It's not like...
And when you do this connection, you see, you have to do it separately. It's not, they're not continuously connected. Let's go back on this one to show that. You literally go from having the cosine of phi equal nearly to 1 and the sine of phi equal to phi to sine of phi equal pi minus phi, that's upside down, and cosine minus 1.
Right.
So you literally change the sign of the whole equation. Now in quantum mechanics it doesn't matter. You don't pay any attention to the zeros of the E in quantum mechanics. But in the classical thing, the omega is very persnickety about what you're doing, and it is not correct to put E here. You have to put E bracket. Absolute. Now we could spend a long time discussing that, so I'm going to move on.
Sure.
But that's the key thing, and this is in the text, part of 4.7, Unit 4, Chapter 7, for your perusal. Now,
But still, this is a bound state problem, right, Dr. Harter? It's a bound state problem, right, for a harmonic oscillator, because...
oh, as far as the Schrodinger goes, you bet.
Yeah, that's it.
Yeah, but the point is that when you have a wiggly potential, there are regions called gap regions
Okay.
where it doesn't act like a bound state. It explodes with distance. So if you just magically drop a wave into that region, it's out of there. It won't live. And remember, the wave functions can't go above a certain amplitude if you're normalizing it. So you have to quit doing Schrodinger mechanics and start doing scattering theory, which is the only honest way to do it, like we do in Bandit. You then sit with various pulses outside and measuring devices on the other side and see what goes through and what doesn't, and what can live in the region with large amplitudes and what has to sneak through like some sort of thief in the night in order to get to the other side. Those are in the gaps. That's the thing you need to get in your head about quantum mechanics, is you're always outside and an inside to every quantum problem.
Even in classical mechanics, this would still be a bound state problem, right? Because E is less than the potential at V at infinity.
Forget the potential for the classical problem. It's useless.
Okay.
Yeah, remember we already said that. You know, it doesn't play a role. The gravity's there, sure, but this is the main thing that's driving it. And the potential, it is time dependent. What good is a time dependent potential when you're talking about resonance? You got to play the game. You can look at this thing that way if you want to, but it doesn't really help that much. Now here is a picture of the bands that occur if I were to have a very jerky arrangement where I hold the pendulum and then I go boom, boom, but I'm very well timed, you see. I go, with this one I go along and I go boom, boom, and then I wait. Boom, 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 boom. That's what this one. This is the bands I get. They're interesting because they cross. And if I do it boom, 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 you know, equally spaced, they cross everywhere. Very interesting stuff. Okay, now you can understand band theory a lot more than you would have if you just read Cattell. He doesn't do this kind of stuff. I don't think he knows this kind of stuff. But here's what we're going to do next. Is we're going to say, okay, I got the band edges. That's like having two pendulums. Okay, our two pendulum thing, right? That's what n = 2 really means. I got a two-state system that it can have symmetry or anti-symmetry. It can have symmetry or it can have anti-symmetry. You've been seeing waves that have either one or the other. Those are the band edges. Brillouin band boundaries, the B states. Things that are labeled with B's here. Okay? The A's are always the same. They're the symmetric ones. Okay? And when they cross, oh boy, all sorts of things happen. But here is the potential is doing this. And now I'm going to let the thing go 6 places and see how many eigenvalues I get for that. I get more eigenvalues now. And most of them are inside here. In fact, all of them are inside there. Okay? And they're labeled with things like E1 and E2. That's what we're going to talk about next, is how you symmetry label for more than 2 pendulums. Okay? 6. We'll pick 6 as an interesting side case. But 3 will be very soon in our discussion. So that's what we have to do next. So the next part of this is wave resonance in cyclic symmetry. Starting with our good old A-B type Hamiltonians. This one being a B type because I'm going to have this not be 0. We have an A for the unit operator and B for the bilaterally symmetric Pauli spinner sigma B. So we're going over a review of that right here. Now the reflection symmetry is defined by sigma B squared equal 1. This is the crazy thing that comes out sane. That is the operator that Pauli uses as opposed to the quaternion B who squares to -1. It's just a difference in a factor of what we are familiar with, I, the square root of -1. But its group properties, its algebra, are very simple, and we're going to apply that algebra again, but this time we're going to show that this Hamiltonian being written as a linear combination of the actual operators that do the transformations is a very powerful way to do resonance theory of any kind. So the next part here of this is just going through that. If sigma b squared equal 1, then sigma b squared -1 equals 0. I can factor that just by I. Sigma b plus 1 times sigma b minus 1. Those are your lowercase p projectors for solving this matrix, and particularly this matrix to start with. Okay, so that's what group theory is all about. Group algebra theory for physicists is all about. Find a way to write your Hamiltonian as a combination of group operators, and then the group operators know all the Feynman paths and where they go forever and ever, and they also know the algebra that will lead you to the eigensolutions. And that's what we're after here. So I simply have to do 1 minus the -1, that's remember the factor that goes underneath the little p projector to make a big P projector. Then I get the idempotent projectors, who are automatically orthonormal. That goes without saying. So there are the modes that you get by applying those projectors to the states. And these states are already defined as group operators, you see. That's what you have to do with every physics problem that has symmetry. If you have that, you immediately find solutions to it, and then you can do all kinds of crazy stuff like we're doing here. So I apply this projection operator to the original state, the number 0 state, and I get a combination. And in fact, I can normalize it if I want to play with states. It's much easier to play with the operators directly. So those are the 2 modes that we saw. Ours were transverse pendulum. This would be the state that we saw if we had them going this way. This one's doing this, and it's anti-symmetric to reflection through here, but it's symmetric if you talk about radial being plus and minus. It's symmetric if you were thinking R. The names can get you in trouble a little bit. This one right here, some people would say this is symmetric motion, and it was for the case that we were transverse, but the longitudinal one, it's anti-symmetric. This is minus that one. The way we're doing the coordinates are pointing this way. If I point the coordinates opposite, this is the anti-symmetric one, and that's the symmetric one down there. Okay, so get used to seeing a character table like this. I think we showed this. This is 1, 1, 1 minus 1, or simply the eigenvalues of the symmetry operator here, symmetric and antisymmetric. And then this is p equals 0 and p equal 1, or simply the points p equals 0 and p equal 1. Or powers, as we'll see later, the powers of the operator. So this is the very simplest character table of a group. And most people don't draw it this way. I've never seen anybody else except us draw a diagram like that. But you pick up any book on group theory, and that's the first character table that you learn about. 1, 1, 1 minus 1. Symmetric and antisymmetric. 0 modulo 2, 1 modulo 2 if you're using this for quantum information theory or classical bit theory. All right, let's do 3. Okay, this is a bunch of masses attached to each other, sliding in and out radially. So now positive is out, negative is in, presumably, for this, but that's up to you. You can label it any way you want. Main thing is you want to use the group operators to take you from mass to mass. And there are 3 operators here. R to the 0th power, R is 120-degree rotation. R to the 1st power, which is the same as R to the minus 2 power. And this one here is the same as R to the 3rd power. And this one right here is R to the 2. That's the same as R to the minus 1 power, the inverse of 120 degrees. So those operators just make a table that is gotten by adding their exponents modulo 3. And that idea of being modulo 3 is really important. So here's the first state is number 0 is this coordinate down here, has a unit displacement of mass point 0. That's the state, that's the base vector state of the classical mode space. That's vector number 1. It's 3-dimensional. This is vector number 2, but I don't number them that. This is vector number 0, and this is vector number 1, unit base state number 1. And this is unit base state number 2. So thinking about this as points around a triangle, this is point 0, 1, and 2. Or thinking of them as exponents of the operator that would take you between them. This is power 0, power 1, exponential power 2 in this multiplication table. So far, so good? Okay? Not the way they usually label group operators, but they should. And then the Hamiltonian, you see, is going to be a combination of coefficients of each of these operators. We're just going to use the group to build the Hamiltonian. So there's a 0th power, there's the 1st power of 120-degree rotation counterclockwise, and there's the 2nd power, which is the same as a clockwise rotation by a 1st power. And there's a picture of them all doing their things to the various kets, base kets, you see. So once you get all this stuff set up, and this is in unit for the 8th chapter of unit 4, and I think that's all I need to say. Now, here's the deal. This is what makes it powerful. We can spectrally resolve H if we can simply resolve R. That is, if we can find the eigenstates and eigenvalues of R, since H is a combination of powers, we will have solved the eigenvalue problem for H.
So which means, okay, they are, if they are operators, then they would commute, right? That's what it means.
All of these operators are going to commute, and this is a special kind of group called an abelian, after Abel group. And Abelian, I don't know, that's a southern pronunciation, abelian groups all have computation of every element with every element. Okay, we're not going to go into the others. That's a separate issue, but not much more complicated now that we've really worked on it. In any case, what we need are the eigenvalues, which are the third roots of unity. We need e to the I integer 2 pi over 3. M is 0, M is 1, M is 2. Does that look like a 2? No, it isn't. It's a minus 1, but minus 1 is equal to 2 modulo 3. So this is modular arithmetic, not just with the stupid bits they use in quantum and classical computing, but with a more sophisticated register that has 3 tristable resonant register of some kind. Which makes you wonder, why the heck are they just looking at 2 all the time? Okay, so 1 equal r to the cube is the main equation for this thing that's giving us roots of unity. 0 equal r cubed minus 1 can be factored. And the values of these row factors here are called irreducible representations. Forget all that funny terminology. They're just roots of the cubic equation. And there it is written as a product of little p projectors. And we have to find the big p's. That'll take us a little bit of thinking, but not much harder than the last time. Okay? We're going to get all 3 orthonormal, whether we normalize them or not, but we're also going to make sure that we put the norm on so that when you add these projectors up, we get 1. That's, you remember, that was a really important part of the matrix theory, linear algebra theory. Well, it applies to group operators too. And once you've done that, each of these p is the eigenvector of the operator, so when I take an r and multiply it by 1, I get r. But when I multiply it by each one of these, I get the eigenvalue of each of these projectors, multiplying them. And then if I do r squared, I get that eigenvalue squared. Okay, so I'm getting these numbers over and over again. And basically, that's what a character table is. It's a collection of the characters that are the characteristic roots of the elements of the group that you're looking at. So, the question is, how do you get the projectors? How do you solve for the projectors in that case? It's really easy with these. This is a subgroup of the unitary group. I simply have to turn those numbers star-wise and flip them. Whatever number's here, I star it and put it down here, and vice versa. So, bingo, there's the projectors. Those are the projectors that are going to produce our eigenvectors and our eigenvalues, too. Okay? So here are the projectors written out in terms of operators. Here they are written out as bras. And those are the actual bra rows that do this. Okay, now I admit, this takes a little bit of study to see what I've done here, but you can see it's really very simple. And some people would call it duck soup. I guess that is an expression for duck dynasty. No, I don't think so. What I call duck dysentery is what that is. Anyway, here is the projectors. There are the bra states I just mentioned. The number I forgot to mention, when I say m sub 3, I mean m modulo 3. Some details about that follows. But anyway, here is a picture of the modes. The phasor modes. You just draw the phasors of each of these complex variables and you have a picture of the modes. And while you're at it, you're also getting the eigenvalues of the Hamiltonian. You have to add those things up. But anyway, here are the details on modulo. Remember when we said n equal 2 for our parametric model? Okay, we meant we had 2 of these things. Now we got it up to 3. So if I wanted to put n equal 3 in there, I would have gotten a whole bunch more eigenvalues when I did that, and I would have to make a bigger matrix to collect those eigenvalues. But when I get things that repeated after 3 bumps, not just after 2. Okay? So right now we've got a symmetry of trigonal symmetry here. Now if you want to put lattice spacings in there, you can do that and make this thing all kosher and connect it with other formulas that you find in places like Catel's book on crystal theory. We have here a crystal that doesn't go very far. It simply goes to the 3rd, and then the 4th one is back home already. Okay, so I think that's enough. Each quantum number also follows a modular arithmetic. Now notice, let's again, our notation. P for position 0, 1, or 2, or P for power of operators 0, 1, or 2. This is the space part of this thing. This is the per space part of the thing. These are the wave number or momentum, the K's, of the wave, the m 0 wave modulo 3, 1 wave modulo 3, 2 waves modulo 3, which is the same as -1 wave, that is a 1 wave going the other way. So all of the wave theory sort of springs out automatically when you take the symmetry road to solving the problems that involve such objects that have that symmetry in question. Okay? A little bit of modular arithmetic. 4 mod 3. Well, it's just the remainder of 4 divided by 3. That's probably the easiest way to say it. What we mean by a 4 mod 3. Okay? All right. Now, what's the dispersion function? Here's the Hamiltonian. Here's one of those m mod 3 states. Okay? Magnetic quantum number is what m stands to too. The mth eigenvalue of r to the pth power. MMRP. Okay? That's e to the I MP. I don't know how to remember. The military police? I don't know. Anyway, M for magnetic quantum number, P for power or position. Okay? M for magnetic, I guess, is where it originated. The Zeeman effect was very, very much a worry for people because they were looking at the solar spectrum and trying to figure out why the lines were funny. Anyway, here is one of them. Here's MP equals 0. Okay? And then there's M times P equal 1. There it is. Okay? And then there is M times 2, power 2. Okay? That's the third one. You're done. That's it. That's the dispersion function. The band, that's the band function. Now it doesn't look like much yet, but you can put any parameters in here you want, and it's right. That's more like it. That's a cosine function. Okay? Now, when we get a lot of symmetry here, like 12, 20, 24, 100, we'll see some of those, what we're going to do is we're going to have a cosine that really looks like a cosine. When you plot this one out, it doesn't look like a cosine. Here are the H eigenvalues and eigenvectors. Now, if we're doing a classical problem, it's K-matrix eigenvalues, right? Then this is equal to omega squared. This is omega for quantum mechanics, not this. This is omega squared for classical mechanics because it's a second order differential equation. Remember, we've been through that already when we talked about the model of connecting those two types of dynamics. So here are the moving eigenwaves. That's what these are. They're complex and they move. They're C-type waves. I've colored them green to indicate that way. These have a stoplight on them. Whenever I mix two guys with the opposite magnetic quantum numbers equally, I will get a standing wave. And here's a symmetric and an anti-symmetric combination. And then there's this guy right here that is stopped all the time. You can't do anything about him. But this one you can make him move, gallop, or not move by taking various combinations of this and this. And that's really interesting too. Very few people talk about that, but they should. So here's the H eigenfrequencies. And here are the K eigenfrequencies. You just put a square root on what you got here, and you get classical mechanics of normal modes. And here's what they look like. If you do the K thing, the square root of that cosine becomes this. And there's straight lines right here, so special relativity, I should say, special pseudo-relativity applies while this thing is straight. And that's what graphene is all about, except it's electronic things that have done this, and that's pretty magical. Phonons do it all the time in the acoustical band, but it behaves like a little mini relativity by having something that has no dispersion, or very little dispersion. It gets worse and worse up here, but if your density of states is all concentrated in 4 pixels here, you can play relativistic games. So you have 2 modes here. These are the standing radial modes, and here's the breathing radial mode, which is this guy at the bottom here. And these two guys are degenerate right now, because I've made just one parameter, one active parameter, because R equals 0 there. Now if I make these complex, something happens. Now this, if it was longitudinal waves, they would look like that. Same dispersion, same basic character table, nothing different there except I made it standing. Now let's do C6, real quick. We've got about 15 minutes at least, I think, left here that we can do some really cool stuff. But we're going to go pretty fast. So this is stuff that you're not going to use in this course that much. But you should know where it is and read it, and I'll give you some references where more can be found. But here's the basic idea. But with C6, I got a lot of ways I can tie the various masses together, that is, couple them. The usual one, called the block coupling, is just the nearest neighbors. And if we're talking about a quantum system, we're talking about a tunneling amplitude between here and here, that's using the same notation. So if I'm really talking about a quantum Hamiltonian, then these are the tunneling amplitudes, which are usually very small. Now, if you're talking about electrons in graphene, you see you're going to have a tunneling amplitude of such and such here, and maybe a different one to another nearby atom. What's magic about graphene is one is very large and the other one is essentially 0. And that's what makes for the crossings. They call it pseudo-relativity. But here we're just doing, shall we say, a molecular vibration problem of benzene, where benzene is confined either to be totally radial or totally longitudinal. If you allow it to do 2, then you have to sort of jack this up by a factor of 2. But it's the same idea. In any case, with this arrangement, there's really only 3 classes of parameters we can think of. First neighbor is what most people think of, and they don't think of those at all. But obviously there are 2 more. Second neighbor connection and third neighbor connection. So the whole Hamiltonian is going to be made up of at least 3 major important parameters besides the one that sits on the diagonal. Okay? So I can have a Hamiltonian where those are the couplings, and you see they have these things that are off diagonal, which really are important. If you take those away, it completely changes the spectrum, because this is totally resonant. You see, all these resonate. They're all equal. Make them unequal, okay, then you can not mess with something that's that far off the diagonal. But this one you cannot play truncation games and just look at that much and hope that you get an answer, like we were doing over there. So, and here's the same situation, except now they're out more, and here they're just sitting there at a weird sort of off-diagonal diagonal. So that's the way Hamiltonians look, okay? Now, here I've noted that these guys could also be present, and right now we're making them real, but they don't have to be real. But this one does. This one has to be real, but this one and this one do not, in order to maintain the symmetry. The reason the other one has to be real is time reversal symmetry is asked for in quantum mechanics. If you don't ask for it, then you can make it non-zero. But anyway, here's a character table where you'd find it in a textbook, except for mine. In mine you'd find this, a phasor picture, a picture of each of the modes. Here's one wave, mod 6. Here's 2 waves, mod 6. Mod means that after 6 we start over again. Here's 3 mod 6. That's what's called a Brillouin band boundary wave, a B-type state. This is a B 1 or 2, depending on some other things that can happen. So it's real. Every one of them is real, plus or minus 1. Every one of these is real, plus 1. Okay? So they're special. This is called A1, this one's called B1. A1, always the same. B means back and forth, back and forth. That's the way I remember it anyway. Okay? And then E, we'll just hold up an E, that means you've got complex numbers for all of them. Now look what happens. I go 1 mod to 2 mod 6, 3 mod 6, 4 mod 6, and 5 mod 6. But this thing's just this thing turned around. This thing right here, 5 mod 6 is the same as minus 1 mod 6. 4 is the same as minus 2 mod 6. And 3 and minus 3 mod 6 are the same. So this one isn't degenerate. These two are. These two guys, 2 and minus 2, and 5 and minus 1, that's this guy and this guy, they're degenerate if I don't make the coefficients of the Hamiltonian complex. Anyway, here's the formula for all the characters of the abelian family. It's really simple. Chi to the magnetic quantum number m at position p, or power p, is equal to e to the 2 pi I over 6 times military police. Pretty simple, huh? That's the Fourier analysis. That's what group 3 is. It's grown-up Fourier analysis and geometry. They've been put together. A shotgun wedding, if you ask most people. Well, you see, to have considered a shotgun wedding, you're going to have to get the shotgun out and make them marry. Okay, so here's what the dispersion function looks like. Same old cosine we had before, except it's only valid at these 6 places, but that's twice as many as we had with 3. Okay, didn't have this one, we had this one for 3. Okay, now that's with block coupling, which is nearest neighbor, first neighbor. Second neighbor, if I take out the first and put in the second, it breaks up into 2 pieces. A 3-like one that's down and an upside down one. You can see how you get a degeneracy of 4 here for that arrangement. And a degeneracy of 2 here, the 0 and 3, mod 6. They're together. They were a singlet before, but now it's a singlet and a singlet, which is a doublet. This is a doublet and a doublet, which is a quartet. Okay? And then, if you make a third neighbor right here, that's just like having 2 diatomic guys that don't talk to each other. That's what you're going to get. You're going to get a doublet and a singlet, which makes a triplet, and you're going to get another one up here. But when you mix these together, that's what you'll get in general for a system that has real parameters, that is a time reversible system. If you make them complex, if R is complex, okay, when they're not, when R is RE to the I phi, the whole cosine shifts. But what you'll notice is the way you get it is you simply take the picture of the hexagon that was the projection of those eigenvalues right here. You see, that's what's so neat, is you just draw a little hexagon here and you get your eigenvalues directly by intersecting with the integers that you're allowed to have. Now I make them complex by putting a little phase in there. It's called the gauge. Put a little vector potential in there. This is called adding a gauge. Okay? That guy's going to move. You're literally going to translate it in momentum space. That's what A does. Remember our classical mechanics. P minus A times a charge or something, right? That's what you get. The gauge moves the bands back and forth depending on how much you want to add of that stuff. Okay? How much curly, Coriolis stuff you want to put on this thing. And this is true of all the things we're going to show. Now we're going to look at and the thing. 6, 7, 8, 9, 10, 11, 12. I like that one because it's a clock. I can tell time, so I make use of that skill. Pretty helpful, right? You're going to have a nearest neighbor, first neighbor K matrix. It goes like that. Don't forget this guy off in the corner there. You take that out and the whole spectrum changes. That's an interesting problem. Here are the roots of unity for 2, 3, 4, 5, 6. We've looked at this one, and we've looked at this one. But those 2 guys have yet to be shown. I'll show a little bit of them. And here we go with a rather bizarre arrangement here of 12. Okay. And here are the character tables. Now this is just writing them out as waves. This is writing them out as phasors, okay? Here's 12, it's pretty hefty. 0 mod 12, 1 mod 12, 2 mod 12. Well, that's Fourier transformation matrix. That's what that is. That is the actual Fourier transform for a 12-member quantum dot system that has, well, it doesn't matter what symmetry it has, this is the way you Fourier transform it. Here's 16, blown up so you can really see it. Power 0 through 16 versus magnetic quantum number modulo 16, 0 through 15. I shouldn't have said 16 up because the 16th power is the 0th power up there. You see the modular arithmetic works on either side of the Fourier transform space. There's the military police, and you just divide by 16. That's the character table. Whole thing. And they're all colored according to phase. You can see a nice rainbow shift here, and you can see here that it's doing it twice, and then 3 times, and so forth, dividing thing up until finally I come back to a rainbow here. What's it look like when you get really big numbers? Like 32. Okay, wow. But you're starting to see some patterns in there, aren't you? There's 64. There's 100. Kind of looks the same, but if you squint, you'll see that 100's a different number than 99. There's 256. You have to stand back a way, and you'll start seeing little sub parts to it. But that's an interesting thing. Anyway, you're seeing the uncertainty hyperbolas. MP equal constant. MP equal constant, right? That makes a hyperbola, equilateral hyperbola in the corners. Interesting. Okay? Position versus space versus per space is what your Fourier transform does. Okay. Now, I'm going to go very quickly through this because this is really outside of our thing, but I want to make sure that you understand that with this you can have a made-to-order dispersion function. The dispersion function is the Fourier transform of the differential equation that gives us the equation of motion. And so you can have all kinds of crazy curves that you want, including, let's say for 6 or 12 or 24, including, well, the cosine is just what you get if you just do nearest neighbor. But you start putting in cross tunneling, and you can get anything you want, including Bohr's parabola. Okay, you can make the thing boring. It turns out it's not boring to do that. These are the numbers you need in order to make those off-diagonal components give you a perfect parabola. And here's why we would like to do that. We'd like to see the generalization of this that I showed you before with the 2-dimensional pendulums, where we started the pendulum with a sum of this and this, which gave me something that had no amplitude on the number 1 pendulum, but the number 0 pendulum had all of it. Right? This plus this gives me big phasor. Okay? That's the time equals 0. Okay? But what we're going to do is we're going to let this phasor turn. Tick, 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 tick. Right? So at a later time, remember this little picture here? With a later time with those 2 guys, this down guy ticking over to here, okay, and this guy up here, this guy right here ticks over to here, okay, and gets added to the other one. You get this one here, and you get this one, I'm sorry, this one on the other number 1 pendulum. Number 0 pendulum is still very big, but number 1 pendulum is starting to grow a little bit. It's got a circle here with this little bit of area that he has stolen from this one. This one doesn't quite have this area. It doesn't look that way here, but if you spot the scale, this one is smaller now by that much. And then he gets a little smaller again, and this one is now sizable. This is at 3/4 beat. Okay, so these beats here, these things are what is the simplest example of what is called a revival. The name is given by Joseph Eberly at Rochester, the great two-level atom guy. He's really the one that opened up the two-level atom for everybody. Before that, it was Feynman, Vernon, Hellworth, and before that was Robbie Ramsey Schwinger, the only papers that dealt with the really wonderful things that a two-state system could do. He took it to a new level, and then he started working on things that showed revivals, which are he found a really hard problem, a really complicated one, so complicated no one could figure out what a revival was. You're going to see what a revival is very clearly. This is the simplest example. It's just a beat. Okay? You start with everything here, and then time goes on. Okay? And I put this as time equals 0 right here. I would go this way where I got them both crosswise, so I'm making a circular polarized state at that place right there. That's a quarter. Okay? This thing right here. Then finally I get to the first beat, which is that thing. That's where I've turned X polarization into Y polarization. Remember this stuff? If not, go back and look at it, because it's really fundamental for all sorts of things. Okay? And then I go get a right circular polarization. Here I get a left. Those are these two cases. Okay? But if you plot the wave that goes with this, you kind of get a little X here. These are the zeros of the real part. So what was existent here has, as time goes on, sort of ghostly gone. The phase is all over the place on a thing like this, and finally it's all reappearing here. It's not like it goes smoothly over. If you just draw a line between this thing, it doesn't look like it didn't, there was nothing here. And then it reappeared. That's the way waves work. That's the way to think about them. Here's an example of a way to see it in motion. And again, we're letting this one be 0 and letting that one turn. Run that again. If I can get my cursor there, I should be able to start this any number of times. Okay? Now this one is done in a very peculiar way, where I've taken this one and literally just imagine it's a wave going this way. I don't have to do that. I can make a standing wave out of it, and it would just follow the phasors that you're seeing there, which is kind of misleading. You've got to be able to realize there are a lot of different ways I could draw the phase in there that would give me the same results at those 2 points. Well, those 3 points. This point is equivalent to that point, right? Okay? All right, what do you get with 3? There's the 3 characters. Here are the states, the revival states. It's kind of a mess, actually, it looks like. I mean, here's one of them going this way, and there's the other one going that way, and there's the guy that just stands still, and they're being added up, and that's what we get. Okay? So when I go down there, let me see if I can show you where the revivals are. They're hard to see. Let me start the thing again. Then I'm going to grab this dot here and take it over to where I think I see a revival. I think I got one right there. No, that's not quite it. I'm looking at the top of this thing. See if I can... No, I think that's pretty close right there. If I stop it right there, let me just put the stop on this thing. I can do that on this. I can just stop it right at there. That's pretty close. It's a little off. I've got one this way. It's not quite there yet. I got one here and one here, right? That's first revival. That's what would be called, in modern terminology, revival. Then I got another one like this, 2/3 of the way through this thing. That's 1/3 of the way through. I go over to about here, and I think I can make the other one. There it is, right there. Okay? That's the same as this one. Okay? All right. Just to give you a feeling for this. Here is 4. Okay? Now, it's got more structure because 4 is divisible by 2. 3 was not divisible by anything except 3 and 1. But this one is divisible by 2, so I get to see my old friend, the C2 revival, hiding in here as a subgroup of the operational C4 group. Okay? So, and then we get revivals in between there. Let's see what the first one looks like. I'll come back here and stop the thing and drag it to the first revival, which would be right around, did I go too far? I think I'm getting there. I think that's about it right there. Yep, that's it. Down another, that one's hiding, and then this one. And then we come back to this one, right? Because this is the same as that one. Okay? So that's what we call revivals, and boy, they get complicated. But if you're a prime number, you don't get any structure. You just get really complicated arrangements of them, which I have not quite yet fathomed about that, but that's something Gauss worried about. For the first 15 years, you might say he thought he wasted the 15 years of his career, because what the hell do you do with Gaussian integers? And that's basically what you're looking at, are Gaussian integers. What you can see from this thing is that it starts out with everything on the 0th power of point, okay? And then as you move along, you can see every once in a while it sort of pops up in other places, like there. Now it's on the number 1 place, and then again later it's sort of on the number 2 place, okay? But there's other stuff is pretty much there. It's not a perfect revival. And then it gets back to the number 1 place again, and then it pops up, I think, in the, well, it didn't pop up very well. It pops up in 1 and 4. And then I see it big time at number 2, which is the middle. I expect that. That one's good. And then 3, I see that pop up pretty well. But 4, that's the best I can do. And then finally, I'll be back at home if I go 1 step more, which would be that right there. So that's what a prime number, one that won't factor. Now you can use these waves to factor integers this way, and that's of course what the quantum information people are trying to do with entangled states. This is just elementary classical waves doing it. Here's 6. It's got a lot of structure. Here's the molecule actually dancing to the tunes there. But here are the various revivals, including, once again, right here, and right here, our old friend C2 revival, because 2 divides 6. And then you'll see the C3 guys in there too. There's the 2 that we looked at for C3 sitting right there. Then we get these new guys that have to do with 6. So you see, this is number theory now. And that's where group theory and all of mathematics really got started, with number theory. So here we're coming full circle. Okay. TC will run you one of these things, and we're just about at the end here. This
we're
is
about
what
30
you get
seconds
when you let
of
the
battery
wave
left.
go full time. Is it out of battery?
A few seconds left.
A few seconds left. Okay, we better go like hell. What I'd like you to see at the end of this lecture is how you do the arithmetic for huge numbers of revivals. And the only way to show the revivals is to look where the wave is not. Where the wave is, these dark lines, those are kind of where the particle is, but there aren't any particles. There's just waves, as far as I'm concerned. You understand things a lot better when you think that way. Nevertheless, I like to track the zeros. This is our old number 2 guy that we talked about. It's just a single x, but then there's a whole bunch of x's already showing up when you have 3 or 4 Fourier components going. So that's like a 3, 4, or 5 level system doing its revivals, but using a continuous wave, kind of like what TC's